Hello. So today I'm going to talk about deep reinforcement learning. In particular, I will be using deep learning to play a self-driving car game called TORCS. So what is reinforcement learning? There are basically three classes of learning. The first one on the left-hand side is supervised learning that you're probably very familiar of. You basically have a lot of images and a labeled data, and then you just put it into model.train, and then it will just get the results. Pretty direct. Another style of the world is unsupervised learning on the right-hand side. It's basically they have no labeled data, there's no feedback, you have to find the hidden structure yourselves. I would say reinforcement learning is somewhere in between of the two. It's basically using reward as a feedback, and it's trying to learn series of actions by experiment with the world. Just like a little kid, you try to play around with the world through the trial and errors. Basically, all in the reinforcement learning, you can frame in terms of agent and environment settings. If you see on the here on the left-hand side, you have a game here. You have an observation OT, and this observation will send to your AI agent, which probably is a neural network on the top, and it do some calculations. It will output you an action AT, and this AT will send back to the environment, which is in this case a game console. And the game console will tell you the intermediate reward, the feedback, RT, and the next observation. So to let me formulate, I would say at step time t, the agent will receive an observation OT, execute an action AT, and receive a reward RT. At the environment, it receives an action A of t, it sends out the next observation OT plus 1, and the next reward. So let me get you a simple concept in the reinforcement learning. It's called states. Basically, states is a series of the experience. So I would say like O1, R1, A1, and then you keep as time goes on, you have OT, RT, and AT. Now, please note that not all the states are fully observable. If you see on the chart, on the game on the left-hand side is a classic game called Breakout. We call this environment is fully observable because you basically look at the game, you pretty much know what's going on. But if you look at the games on the right-hand side, which is called Doom, it is not fully observable. Why? Because you look at the screen, but you don't know what is happened at the back. Maybe there's an enemy behind that. And we call this game is called partially observable environment. And this is a very difficult problem to solve in the reinforcement learning. There are basically three approaches in the reinforcement learning: a value-based approach, a policy-based approach, and a model-based approach. And I will quickly explain to you what are these in the next 15 minutes. Why people are so excited about reinforcement learning? You heard about a lot of reinforcement learning in the morning section. The reason is because we found that if we combine reinforcement learning and the deep learning together, we have a good chance that we are able to create a good AI system. Like in this example, I just have my car racing game, and I just input my screen pixel or whatever the states into my deep neural network, and the network will calculate, and by learning the experience, and it gives me my output like steering, gas pedal, and brake. And it's pretty general and not just only applied to the games, but can be applied to other problems. And that's why it's a very promising field in the future. To give you some context for the discussion, let me discuss one term called policies. A policy is basically an agent's behavior. It simply said that it maps from states to the action. In mathematics, we say that the policy is called pi, and then you have a state S, and then you basically calculate, it tells me the action. Now, how do you simply understand this? So you look at the table on the right-hand side. It's quite easy, right? Let's say if you're in the state of at the corner, your action most likely will be take a turn. And if your state is near an obstacle, you most likely will hit a brake. And if, of course, if the car is on the straight line, you just go accelerate. In the reinforcement learning, there's only one single goal, is to try to maximize the sum of the future reward. So the goal we're trying to do is to choose an action AT such that my future expected reward, total, big RT is equals to RT plus 1 plus gamma plus RT plus 2 and plus going forward. Now you can see this is a discount factor gamma here. why there's a gamma factor? There's two reasons. Number one, as intuitively as time is going forward, you are more uncertain about your reward because you're just not sure about the future. So we have a discount factor here. And the second reason, there's a mathematical convenience, which we will come to that point later. But let me just assume that first. So the first part I would like to talk about is called the value-based reinforcement learning. The idea of the value-based reinforcement learning is try to estimate the optimal value function called Q. So what is a Q function? What is a value function? If you look at the papers, people are about Q function, value function all day long. So a value function is a prediction of a future reward, i.e., it says that how much reward I will get in the action A and in the state S. So a Q value function, it gives me the expected total reward from a state S, which is your current screen, and your action under some policy pi. So in mathematics, we can write down as my Q function as a sum of the future reward under sum of the expectation of my policy. Now, once you have this Q function, you are able to achieve optimally by always choosing the optimal state action 8. Now, this formula looks very complicated, but I will give you a very simple understanding what is meant by Q function intuitively. The best way to understand the Q function is consider a strategy guide. Suppose you are playing this very difficult game called Doom again, and I don't know how to play it, but that is very easy. If you have this strategy guide, I just go to the right-hand side, go to the website, look at the, and what I do, then I just follow it. It's the same. If you're in the state S, and you need to make a decision, then it's become very easy. Once you have this magical Q function, then you just pick the action with the highest Q value. Then it will do the job for you. Now, it looks pretty magic. Then the question is, how to find this Q function? As I previously defined, the discounted future reward, RT, is sum of my total future reward with this discount factor, which I can, on the second equation, I can written as my big RT is equals to current reward plus gamma of my future total reward at next time t plus 1. Now, however, if you recall my previous discussion that the definition of the Q function is to choose the maximum reward if we in the action A and the state S. So we can write my Q function on the third equation that my QSA of t is the maximum of my total return. Then I can rewrite my Q function on the equation number 4 is that the current Q value is equals to intermediate reward RT plus my next Q function as long as I choose the maximum value of Q. So in the plain English, we say that the maximum future reward at state S and action A is the intermediate reward R plus the maximum future reward in the next state. Now this equation, once we have this equation, then we are able to solve it by finding this Q function using dynamic programming approach or iterative method to find this Q function. So you may ask, actually Q function has been there for since 1990s. Why people talk about Q function again? The most recent breakthrough in 2013 and 2014 is called the deep Q network. Basically, we try to combine the Q learning and the deep learning together. As you see, if I try to write down all my Q function on the table on the left, if I write down my state and actions and write down all my value for such a complicated game, the table will causing millions of lines and it's impossible to check what's going on. The idea recently we have, in particular DeepMind has a breakthrough is using this called DQN idea. I basically say that I'm using a new network to replace this big Q table, i.e. I'm using my new network, using a weight W to compress my Q table. So instead of looking my table Q function, the training is turned slightly. It's trying to find the optimal set of weights W to train my neural network. In the literature, you often call this called nonlinear function approximations. So we have went through a lot of mathematics, so let's look at some demo. This is one of the demo I do on my laptop. Basically, it's a maze in the dome, and there's a lot of toxic there. And the only instructions I give to my AI agent is to pick up the health. Once you pick up the health box, you got 1 point. Otherwise, you just have no reward. And I train this neural network for maybe 2-3 hours, and let's see what it does for me. So this maze is pretty random. It tries to stuck here, and then it starts to find out the health box, and we try to keep looking and try to make himself survive, because if you don't pick up the health box, and then you can see at the corner, it will automatically make 100-degree turns and try to keep finding this health box to make it survive by himself. And this is pretty amazing, because I did not teach my AI how my maze is designed or how do I get the solution. There's no if and else in the code. I just ask the AI agent, you will go score 0.1 if you pick up the health box. So I just went through the value-based reinforcement learning. The second part I would like to talk about is called policy-based reinforcement learning. A policy-based reinforcement learning is trying to directly find the optimal policy pie by searching directly. So what does it mean? Let me just review. In the previous slide, we have mentioned that a policy is the agent behavior. It is trying to map from a state to an action. So I have a screen input S, I feed into my policy, and the policy will tell me what action I should take at that state. Now we can actually directly search the policy by directly parameterize the policy by some model parameters theta. So I can write down my function pi policy as a function of S and theta, which is model parameter. And it just output my action AT. We call this is a policy-based reinforcement learning because we will adjust these model parameters directly. And the goal is to maximize my total reward from the beginning. So at the last equation, I said, I try to maximize my total reward. Big R is equals to R1 plus R2 plus R3 going forward. So how can I make a good action more likely? Just like when you try to teach a little kid, you want to educate the kid to take some good policy. So how should I do that? The most obvious way to do is to define an objective function, right? Everyone has objectives. So we define an objective function on this equation is L theta, which is sum of my total reward from the beginning to the end under the policy pi. In short, I can write them as L theta is equal to big R under some expectation of probability distribution. But the mathematics is not important. The goal, what we are trying to do, is to maximize this reward, right? So how do I maximize this reward? If you remember your high school mathematics, that's easy. I take a gradient. I take the gradient of my objective function L with respect my model parameters theta to try to maximize my function. So how can I do this? Now, without going all this formula, let's just focus the last equation, because the derived you can read elsewhere. It says that the gradient of the policy is equals to 2 terms. The first term is called dq/dA. In English, it says that how is my Q value function change as my action is changing? So if I change my action a little bit, how is my Q value changes? And the second term is called dA d theta. It's basically saying that how is my action output change as long as my model parameters change. Now, the left-hand side of the equation, it tells you how to update my neural network, because once you have the gradient, I know how to update my neural network. And the right-hand side of the equation, it tells me to update the neural network, I only need 2 things, which is the derivative of Q with respect to A and the A with respect to the theta. If you step back and think about that, this equation is actually quite impressive. Why I say so? Because this equation does not depend on any model dynamics. I.e., this equation can be applied to AlphaGo, it can be applied to self-driving car games, it can apply to Atari games, it can apply to your company, advertising company, I need to optimize this solution. as long as I can fit into this reinforcement learning formula, then I can able to solve the optimal policy pi. And this is the power of the policy gradient, because it does not require any domain knowledge. For example, if you look at AlphaGo, when they try to program AlphaGo, they do not pre-program any domain knowledge about how Go is played. The way they do is they self-play, they set up two AlphaGo, they self-play each other using the reinforcement learning, try to optimize this model parameters theta such that it maximizes the reward, which is the probability of winning. And this is pretty powerful, in my opinion. So let's step back to have an intuition. We have talked about the value reinforcement learning. We also talk about policy reinforcement learning. How do I link up between these two? The way I see is like a teacher and a student. A value-based reinforcement learning is similar to a driving instructor. When a student taking some actions, the teacher will just give ticks or cross according to the action, and I give you a cue values to assign how good your action is taken. A policy-based reinforcement learning is just say, okay, I don't care about the kill function. I sit on the car, I just want to drive it well. Give me the policy, how to drive it well. So it's two different approach to the reinforcement learning. As a matter of fact, people try to combine the two together. You can see on the chart on the left-hand side. On the left-hand side is a value-based policy, and the right-hand side is a policy-based gradient. And people try to combine together. We call this actor-critic approach. It's like teacher-student relationship. The teacher will give a student a score by using a Q function, and then the student will try to learn the policy based on the feedback by the teacher. So we talk about so many mathematics. So how can we apply into these self-driving car games? This is called TORCS. It's a state-of-the-art open source simulator car racing game written in C++. The main features, they have sophisticated dynamics. It can provide several tracks and controllers. And they have a lot of sensors reading, for example, like range finders, laser range finders. They have a speed meter. They have the position on the tracks. They also have like rotation speed of the wheels, angle with the tracks, and other variables. And this is quite realistic to many self-driving cars you can find in like Uber or Google. And we try to do the same simulation though. Now the deep learning recipe for all the reinforcement learning is very similar. On the left-hand side, you have a lot of game input state S, like rangefinder readings, speed of the car, the road position of the tracks, RPMs, blah, blah, blah. I input all these state variable, which is called the states. I input into this neural network. And this neural network will try to interact with the environment many, many times, try to get the reward, and try to compute the optimal policy pi using the policy gradient. And the output of my neural network will be just three numbers: steering angles, how much I want to hit on the gas pedals, and how much brake I want to hit on. Now we have talked about the reward function and objectives, but we have not discussed what is the reward function in this case. The obvious choice, because we are trying to making a self-driving racing cars, the obvious choice is try to make the car as fast as you can. So an obvious choice is to return my reward function is V car cosine theta, which is basically go straight as fast as you can. However, experiment is found out that this learning method is not very stable. So I actually modify this reward function a little bit by accepting I want to car drive as far as I can, but I also penalize a little bit as long as the car is not staying at the center of the track or when your V sine theta is too big, which is a reasonable assumption because if you, when you try to learn driving, your teacher will often say that just stay center of the track. It makes sense. The source code is actually available, so you can actually go to Google and search for the keyword DDPG carrots. So DDPG is the policy gradient that I just mentioned. Carrot is the software code I use to programming this. So you just Google it. The source code is on the internet. Feel free to download it, test it out, and understand it. So let me just give you some demo. So the demo, as all other machine learning algorithms, you start with a training data set. So I choose a track called Aalborg tracks, and I just keep training for like few hours, and this is what it learns. You can see some engine sounds. And then you can see the car is trying to try at the center of the tracks, and it's trying to drive slowly and turn the corner and try his best to drive, and so far so good, I would say. However, as in all other machine learning algorithms, it is very important you don't test your results on the training data set. You also make sure you validate your results on the validation data set. So what I do is, after I train my neural network, I ask the car to drive a completely different track. The car never seen it before, and see how it drives. You don't want to make sure that your neural network does not overfit. As a very interesting fact is that if you look at a lot of reinforcement learning papers, they often show you training data set result is so good, but they never show you a validation data set results. So I'm going to prove that it actually works. So this is a validation data set. It's a completely different one, and it's trying to drive. It's trying to go straight, and then now you can see there's a little bit waggle. And actually, I found that this waggle is quite common in a lot of reinforcement learning agent. I actually spoke to the guys at Uber AI. They actually see a similar behavior as me. So I think this is some limitation in the neural network that we need the researcher to continue to find out why is that. But you can see the car is actually able to drive on a completely different tracks without any problems. Now, we come up with a very tricky question here. Is because I asked my AI car to drive as far as I can, then it come up with a tricky question. What I found is that the AI agent does not want to hit the brake at all. That is quite a tough problem. It took me a while to understand, and why it kind of makes sense, because if you try to hit the brake, the car just slow down and you say, that's go against with my reward function. Of course, I don't want to hit the brake. So the way I try to solve this problem is using called stochastic brake idea. It's basically, you think about it as a human. When you try to learn driving a car, your teacher will say that, hey, don't hit your brake too hard. Try to feel the brake, right? Feel the brake and see where is the contact point. So I using this idea, I tell my AI agent, during the training phase of the training phase, I ask them to try to hit the brake in the maybe 10% or 20% of the time. Try to get a feel of the brake. And this is, after this idea, I'm using the same training set, and it's actually able to drive and finally learns how to brake. So you can see now it's driving like 150 kilometers. Around a sharp corner, it brakes to 50 and then try to accelerate again. So this time it looked a bit smarter than the first demo that I showed to you. And it's trying to slow down. And now I see a straight line. Then, okay, I drive and I slow down a corner. And then I try to drive again. And okay, this is a bit tough corner, so I slow down and cautious driving. Okay, now it's keep going. Actually a bit dumb, but it's coming, driving. So that is one way. So that's why I like reinforcement learning, because you can actually visualize the results rather than just looking at like validation laws or training laws, just a bunch of numbers. You can actually visualize the result, why this AI agent can do it well and what is not doing well, and then you can drill down into the code and try to understand. So this is the last demo I would like to show you. In the reward function that I mentioned, that I have request the car to be stay at the center of the track. But in fact, this is not a necessary requirement, because as you know, a lot of F1 drivers, they always try to turn the corner. They try to walk in the apex because that is the fastest route. I would like to check if the AI agent able to learn this. So after I train my AI agent able to drive the track in a decent manner, then I remove the reward function. I just ask, drive as far as you can and see what it learns. So this is the last demo. So you can see this is already 200 kilometers driving on a straight line, and it's trying to pass the first corner. You can see it's actually going to the middle of the corner and try to make a shortcut. And it's trying to accelerate again, and it try to not stay at the corner, try to using the apex to make the turn and try to speed up the car. And this is quite a difficult track, as you can see, because the car is driving reasonably fast, and it's trying to learn how to find the shortest distance to drive the cars as far as I can. Now, this is a pretty fast, like 200 kilometers, and try to slow down, it brakes, and it's trying to make the corner turn. And this is a pretty difficult one. It's trying to drive at the straight line as far as I can, and then there's a sharp U-turn corner. And you can see it's able to turn, slow down to the 60, and then make a turn. So, sorry, the sound was a bit bad because my computer is still a non-SSD hard drive. So I try to record the video. The hard drive is not fast enough. So unfortunately, I'm not like Google, which has a lot of like computing farm to do this research. I only have a poor 5-year-old laptop to do it. So please apologize if the video content is not that great. But the policy is not too bad though. So what are the future applications? Obviously, self-driving car is certainly one of the very big business. A lot of big companies, Uber, Google, Tesla, IBM is getting into this business. And you can see because they also observe these laser radars, ultra sensors, video screen, and try to learn the policy. And as long as we have more data, the policy will be getting better and better. And I believe the policy gradient not just apply to the self-driving cars, but it can be into many different areas, like maybe household cleaning agents, nano robots, or try to handle dangerous environments. It can apply using policy gradient method to many areas. As I said, the policy gradient does not require your model dynamics. That's why I believe reinforcement learning combined with deep learning together is the future of the AI in my view. And this is the end of my talk, and this is my Twitter, so you can follow me if you want to. Thank you.